Hello and welcome to Database Design Chat number 16. Tonight, I'm going to talk about acid. Okay, not that kind of acid. We're not going to be burning anything. This is not Mr. Science. Okay, not going to happen. It's also not any kind of acid. We're talking about the acid that defines the four major characteristics of a relational database, what the engine gives us, and what we're really after when we're using a relational database. It's been a while since I've done one of these chats. I'm doing as good as I can. Tonight's chat, well, let me just back that up. Next week's chat, the next chat I'm going to do from a theme park. I've got on my Disney shirt here. The mountains are calling. Thunder, space, and splash. Everest is really calling me. That's the one that calls me the most. But I'm going to be going to Dollywood this weekend. I'm going to do my next presentation from there. I'm going to make that happen. I've been talking about doing it for a long time. This time I'm going to do it. If I don't do it this week, it'll be the next week. It'll be the next time I come on here, one way or another. And before we get started, let's just say a little bit here. I'm Lewis Davidson, Dr. SQL. You can find me at DRSQL all over the place. Just go to the link tree. You can catch my Dollywood, my Disney. Stuff is linked there. I do some other stuff other than SQL. Mostly I do SQL though. From a day job, from a fun. All right, so what is ACID? ACID is four characteristics that make a database a database. With atomic operations, consistent operation, isolated operations, and durable operations. Let's talk about each one of those individually. Atomicity is something we've talked about several times before in our discussions, and it's all about making singular operations out of multiple operations. So if we have like 10 things that have to occur, they all have to work together. They have to finish and succeed, or none of them succeed. Okay? It has the same general meaning, exactly what we've talked about in the past. So what I want to do here is I'm going to bring up a screen and show you some statements, and we'll talk about what atomic operations are in this set of statements. So when we look at a bunch of statements like this, you might think that this statement right here, this begin schema test, is a one individual statement, and it is technically one individual statement in SQL. But to actually make that operation happen, think about all the things that have to occur. So you run create table, schema test, test ID, value. The table has to be created. Then the test ID row has to be created in the columns. The value ID value column has to be added. Not only that, but you have to go into the structures and actually make the physical structures. So all those things have to occur. If you get to the very last statement that's not in the not SQL code, but in the C# code that's written, maybe even binary code, maybe even machine code, and you've gotten to that end and you run out of disk, well, you don't end up leaving test ID out there and value, and the table looks like it's there, but it's not there. It all has to be rolled back. So we have to make sure that's possible. Now, when we are looking at this, we also need to be able to say multiple statements are one. So when I do begin transaction, I insert into this table, I insert the next rows into the table, and I commit transaction. If any of this stuff fails, for any reason the commit transaction fails, or the insert fails, or that insert fails, or that begin transaction fails, we have to say none of it occurs. So we have our own control where we can say this is an atomic operation or it's not an atomic operation. And this is where a lot of people have some really bad coding issues because they don't use transactions, or they do things like this, just like what I have right here. What's wrong with these four statements? Well, not every single statement will stop a transaction. You may run insert into schema test and it fails, but it may keep running because not every single error kills the transaction. A check constraint, I believe, doesn't in the transaction. It doesn't really matter which ones. Just take it for fact. Some errors do not stop the processing. It doesn't keep it keeps going. Or sometimes you'll do it and you'll forget to put the commit in there. And then what happens? You get blocking because that atomic operation is still open. I once had an occurrence where I didn't close a transaction. I wrote some code like this. A statement failed, and the front end stopped processing. And we kept operating on the same connection the entire day. So thousands and thousands and thousands of these transactions were being captured, but I could never commit them because they were on a transaction in a connection I didn't have access to. So we lost an entire day's work because someone asked me what was the dumbest thing I've done. What the dumbest mistake I made just recently. I forgot about that one. That one was good. That was about 20 years ago that happened. Okay, so atomic. Everything has to happen or nothing happens. And keep in mind, even one statement like insert into, this statement right here, this insert into statement, there's so many operations occurring in there. You just can't, each column value is going to be a step, right? All the stuff, we talk a lot about writing set-based code in SQL, but that does not get translated to set-based code in the back end, right? That our relational code, our declarative code says, go create some data, do that for me. And then it goes, does it, and about a million things later, it says, okay, I'm done. But it's not just one operation, and all those things have to be undone if something happens. Okay, let's talk about the next step. Okay, so that's atomicity. Let's move along to the next one. This is consistency. What consistency means is when I finish a transaction, when I create that table, when I begin a transaction, and I commit a transaction, when I insert a row, when that transaction ends, when I've given it back to the customer or the user and it says done, it needs to satisfy all of the things that are true. If it's an integer column, it needs to be an integer. If there's a check constraint, it needs to be covered. Everything needs to be consistent. Okay, so let's take a look at that. All right, so we go to this operation we had here. When I get finished creating this table has to be created and it needs to work like we expect. That one's simple enough. But look at the conditions here. I've got a primary key. I've got a check constraint. Value has to be greater than 0. Okay, one of COD's rules is, there's no subversive language. There's no way to get around these constraints. There's no way to go behind the scenes and fiddle with it such that a value -1 is in there. I'll talk a lot more about constraints one day, and we'll look at the settings and how you deal with them. And I just want to make sure it's clear. When you're done with the transaction, that check value has got to be greater than 0. It doesn't necessarily have to be checked while you're processing. Okay, so SQL Server actually does this. It makes sure the value is greater than 0. There's no intermediate steps you can take that can put a value in that column that's greater than 0. But that's not necessarily how it has to be. All it has to be is when you hit commit transaction. So we do begin transaction. We insert this value in here, 1, 1. We insert 2, 1. No matter what we do, this value of 1 is greater than 0. We know that. But there's no way I could have put a -1 in there or a 0 or a -2 billion and it break the code. At the end of this transaction, when we commit it, we know that every rule we set up in the database will be followed. And this, to me, is one of the things that makes me love relational databases the most. Because I know what I put in. I know that it's going to follow the rules. And I've set up these rules in a way that I don't get bad data. Sometimes it may take a little longer. You can argue that check constraints take more time and forward keys take more time, and they do take more time. But I'm willing to pay that price for not having to go, why is this query not matching this query? And it turns out because someone didn't put a foreign key constraint and someone forgot a condition. Okay, so all of those things I've told the database, this must be true, alternate keys as well. They're done at the end of the transaction. All right, next is isolation. And this means that operations within a transaction are isolated from one another as much as they need to be. And there's always an argument, what does that mean? How much does it need to be isolated from another transaction? And this can be argued a lot, but generally speaking, we want one transaction that's occurring to not be able to have an ill effect on another transaction. So that goes both ways. Let's look at the slide. Let's look at the queries. When we're creating this table, can other people query it yet? Right? We don't want that. So that's an easy isolation. There's a thing called a schema lock, and it blocks people from using the schema you're making changes to. But let's think about our transaction here where we're writing data. And user number one, it goes out and you run this query. Somebody else writes a select statement, and they're trying to read the data in our table. Should they be able to? What if they read part of the data? What if the data rolls back? What's the value there? So we need to isolate, one transaction from another. And in this case, I don't want anybody looking at the data that I'm inserting while I'm inserting it. But what if I'm also then querying other data? Maybe I have a trigger on this table. I wrote a trigger today. Triggers are not the worst thing in the world. They're not the best thing in the world. Use them judiciously. But what if there's a trigger on this table and it goes out and it reads another table and says, oh, what's this? And does something. Do you want that transaction to affect this transaction, right? Somebody else's transaction. What if two people are inserting the data? Like two people start a transaction and they both insert test ID 1. How the system works in SQL Server is it doesn't let two queries have the exact same values at the exact same time. We have two kind of concurrency methods, and we'll talk more about this later, but we use either versions, so I can see versions of the data as it was in the past. So if two queries insert into the data, insert into schema name test, two value 1s and two value 2s, using a version control, then it lets them, and then it checks it at commit time. That's using the in-memory memory optimized tables in SQL Server. Not most people are going to use those for many things because memory is still it's not expensive comparatively to what it used to be, but it's also not that cheap. I mean, we're not going to have terabytes of RAM on our servers for a lot of people. The most typical kind of way is they use locking. So one connection does a begin transaction, then the next thing does an insert into schema test, and it sets the value to 1 for the primary key. Another transaction comes in and writes the exact same code. It turns out a failure, even though that's not a committed data. If data's not been committed, it's not considered real data, but it does hang out in the system in the physical tables that you're going to access. And the one thing there is the other connection might have some timing issues. I'm going to talk about that a lot more in the future. Concurrency problems are strangely enough something people don't think enough about, but they're really the main problem you're going to have writing these things, because that's where the problems come in. The timing of writing two queries, we can isolate them from one another. Okay, two per connection start a transaction and they do something. When we're using locks, one may succeed and the other may wait until they finish. So they may do a bunch of stuff and then they commit and they let go of their lock and the next connection can work. That kind of isolation is great, except then the other transaction doesn't know what happened in the other transaction, and you have to make sure you code for that. So isolation is mechanically part of the RDBMS system that isolates things, so we make sure we don't step on each other. But it also is something you're going to have to take care of yourself in some respects. What I want to make sure is clear here is that you can override this in the definition. Note I said a transaction must be suitably isolated. Not every transaction has to be isolated completely from one another. Two queries writing select statements can both run select statements, just reading data. But when you start adding writers in there, then can the data be read? That's where we look at the different kinds of concurrency controls. Very, very important stuff, especially if you're writing any kind of code where the data matters. Okay, and I'm joking, but if you're writing a CRM system and maybe you mess up the customer's phone number because somebody wrote the data at a different time, you overwrite it. That's kind of bad. When you're calling the wrong person, you lose a sale. But some people actually are going to write code that does medical stuff, and you may have two people writing a pump, and they set that up, and it starts writing data that it's doing something, and you start ignoring it, and you get two or three people giving patients the same medicine because of concurrency problems. That's not good. It's just not good. You don't want that to happen. All right, so the last topic is durability. And durability goes to the fact that when I put a transaction in and I commit that transaction, I expect that darn thing to be there when I come back. Because that's what I've said. That's the whole goal of writing data. And this one's tricky because there's a lot of layers to durability. First, when I commit, it needs to be written to disk. When I do that begin tran, insert into commit. I'm not going to show the slides again. I'm going to send the code again. So when you hit that commit transaction, you expect it to be there when you come back. But there's a bunch of things that can happen between the time you write that commit statement and the time the server crashes, right? It should be written to disk. Every transaction, even memory optimized transactions, are written to disk before you hit commit transaction if you ask for it to be. It used to be the only way it could be done. There's two ways you can get around that synchronous call to the disk, to write the disk. You can use delayed durability. Delayed durability says as soon as it's written to memory, all SQL Server writes or go to memory first. That's the place where they're at, and then they get cached to disk. Memory optimized does it one way. In regular disk-based tables do it another way, but that's the foundation. It's got to be written to memory. It's got to be written to disk. Commit. As I said, everything has multiple steps. That's what the transaction log is for, right? So it has to be written to that transaction log. It has to be written to memory. Then it can be flushed to disk later, asynchronously. In I think 2015, 2005. I mean, maybe it could have been a little later than that. Certainly for the last any supportable version of SQL Server has a function called a setting called delayed durability. and it lets you make that write to the log asynchronous. So it doesn't have to write it to disk at all, anywhere. It just writes it in memory and goes back. The log write is asynchronous. So the customer may write it to the transaction, they may write it, and they get control back, and they think it's done. Even after you put the disk, if that disk crashes, one of the disk crashes, you haven't backed it up, it's not necessarily durable in that case. If you've written it to disk and both disks crashed, failure, then you've backed it up. You've got it back up. You got it backed up on the same machine. Something that crashes, go on, right? You can always lose an entire machine. We've all done it. It's not typical, but it can happen. And then you get it to back up. Once it's off, once it's saved off of your machine onto a transaction log backup or a differential backup or a full backup, then it's really durable. But we expect it to be durable. We expect it to be saved. And once it's to the disk, it's considered durable. One of the things that memory optimized tables give you that's really cool is non-durable tables that you write it's just written to memory, and that's it. If the server turns off, the data goes off. And that's cool because the uses you would use a table like that are transitory data, session data, things like that. So it's gone. Okay, we've got these 4 principles that are really fundamental. We know we can write these operations, and when they're done, the data is consistent. All the steps are treated as an atomic step. We know it's isolated. We know that we didn't read across into some other data that's not there. We wrote a rule that said, you have to have a foreign key value. When you get back that foreign key value, when you commit, that darn thing is done. That foreign key is there. It doesn't have to exist a few minutes from now because it may be deleted and there's things that may occur. Your row may be deleted just as part of the next transaction that was blocked until you finished. It may be deleting your data. That's okay. That's not our problem. That's a different atomic operation. That's the thing that makes debugging code fun, is all things that can occur. And then we know it's durable. All these things have occurred. So happiness. This is when you're done and you know what's happening to you. Okay. I get through that. All right, until next time. It's gonna be outside. I'm gonna do that. I'm not forgetting again. I've forgotten that to do it several times. Rain, busy, hanging out with people. Correctness starts with proper structure. All those things we talked about. Atomic transactions. Building your database right, you'll have the right number of atomic operations to occur. Like if you have an invoice and invoice line items, I may want those all written as one operation. I don't put them into one table so I don't have to write a transaction. Okay, that's illogical. That does not compute. Correctness gets into how you write your code. I want that to be a little bit clear, hopefully. As we talk about, isolation, especially, that property really starts to talk to, what kind of things can occur if I don't write my code right. And that's, obvious. So these are not always provided by other database platforms. And the big point there, it's in little words, is they're not always needed. And that's the kind of stuff that gives a relational programmer nightmares, right? One of the things we've kind of built up our platform in is we know what a relational database can do. Why would you not want this? Well, sometimes you don't really care about the data in the same way as you do for a relational database. And there's a lot of overhead. The scale out is a lot harder on a SQL Server than it is on some databases, because we have this consistency. That consistency model is firm, and we know if the data is right. If we put in 2 rows, we get 2 rows back out. If we have a foreign key, we know it's there. And some other platforms have eventual consistency. The data isn't necessarily there immediately. And things like forum posts and things like that, it doesn't matter that you've got these in disparate places and they eventually mesh up and you eventually get things correct. I do a lot of YouTube chats with some of our Disney friends. And if I'm watching the chat, I might be typing, my wife's typing over here, and the order of the chat for me is different than the order of chat for her, because it gets inserted here and then it gets propagated out to all the other clients. That's fine. If we're talking about a chat on YouTube, that's totally cool. If we're talking about a set of transactions or a logs or something that has to be right, we're going to use SQL Server. We're going to use this gotta be consistent thing. But then our scaling up is more here than scaling out. It's a trade-off to get the values of the asset. I love that. That acronym is awesome. All right, so I hope this has been useful. It's been a lot longer than I expected it to be. They always are. If you have any questions, please send them to me. I'd like to hear your questions, your comments, your feelings. I would love to add an episode. I would love to have you on the show to talk about database design stuff. I'm totally willing to do that. So just hit me up and let's talk. Till next time, I'm Lewis, and this has been another Database Design Chat. I will see you in the funny papers.